Welcome back to our journey here. Today we're going to use quantum mechanics to identify electron configurations. In our previous video, we introduced the Bohr model of the atom, which is great if we have a single electron in our atom. This is not really true for things beyond hydrogen, so we need to introduce a better system. Our better theory is known as quantum mechanics. Quantum mechanics is a ton of fun to get into, really fun to study. Unfortunately for us, it's a very high-level topic which requires lots of calculus and lots of chemistry knowledge. So we're going to leave it for now, but we'll try to wrap our minds around at least the basic ideas and what conclusions we can draw from it. In our quantum mechanics, we no longer have electrons in orbits. Instead, we have electrons in orbitals. These orbitals describe where our electron is likely to be, but it is probability based. Quantum mechanics leads to some of these weird phenomena where it's hard to really wrap our mind around and understand exactly what's going on down at this scale of atoms and electrons. One of these strange properties is wave-particle duality. We've been drawing electrons sometimes as little dots that orbit the nucleus. Well, that's not really true. Our electrons aren't really particles, but they're also not quite waves. They're somehow in between a wave and a particle, or sometimes behave like a particle and sometimes behave like a wave. To handle this, quantum mechanics uses wave functions, an advanced mathematical technique, which we can try to interpret as the probability distribution of our electrons, probability that they occupy a certain space. All right, now that we're properly confused by all that terminology, let's try to picture, well, what does quantum mechanics actually tell us about the electrons in our atom? Well, we can still imagine our atom as a nucleus that is very, very, very tiny, containing our protons and neutrons. The rest of our atom is mostly empty space, occupied by those electrons. But now, in quantum mechanics, our electrons exist in orbitals. These orbitals are our homes for electrons. They're three-dimensional shapes where the electrons are at least most likely to occupy. Our atoms have lots of these orbitals. These orbital electron homes can be empty, they can be partially filled, they can be completely filled, but every atom has them. Our orbitals have different energy levels, they have different shapes, and they come in different varieties. Some as a set of 1, some as a set of 3, some as a set of 5, and some as a set of 7. Our job is to look at these orbitals and decide for any given atom which orbitals have electrons and how many. If our electrons live in these orbitals, well, we can try to classify them just like we can classify apartments. If you're trying to give directions to an apartment, you need to know, well, not just the building, but you need to know the floor and you need to know the unit on that floor. We can do the same thing with our electrons. We need to know what energy level they're on. That would be like the floor. We also need to know what shape orbital they're in. This is like, well, what unit are they in? Are they in the corner apartment or not the corner apartment? We can do that by labeling our orbitals, giving them a code name. Our code name is going to have a number followed by a letter. That number tells you the energy level, tells you what floor you're living on. The letter is going to tell you the shape, tell you which unit that you're in. We have some examples. We could have a 1s orbital. We could have a 3p orbital. We could have a 3s orbital, a 4d orbital. right? We have lots of different combinations of numbers and letters, and they're all going to lead you to different places, different apartments, different orbitals. We said these orbitals are strange and probability based. One way to imagine this is like you would a strike zone from a baseball pitcher. If a baseball pitcher is throwing at the catcher's glove, they're not going to be 100% accurate, but a professional pitcher is going to be pretty good. Before the pitch happens, you can have some expectation of where that ball is going to go. Do we know exactly where it's going to go? No, no one's perfect. But we can have a distribution of what are the most likely outcomes. Well, maybe 20% of the time we're going to get it right on target. Some percent of the time we're going to be a little bit off target. And then maybe once out of every 1,000, it might go over everyone's head into the stands. But we have this arrangement of outcomes. Some are more likely than others. If you're trying to predict where the ball is going to end up, we can at least have a pretty good idea. We can do the same thing with our electrons. Their position is going to be probability based as well. We can try to come up with a strike zone for where our electrons are likely to be. One way to do this is by taking a picture of our electron many times. Here, each dot on our picture is one snapshot of our electron, or maybe one pitch that the pitcher throws at the catcher. Most of the time, our electron is close to the center. Occasionally, it's further out. And maybe once randomly, our electron is hanging out really far away from that nucleus. It's not impossible, but it's unlikely. Unfortunately, this is how we have to think about our electrons. We don't get to be exactly certain where it's going to be, but we can try to draw a strike zone, a shape, where our electron is going to be at least 90% of the time. We can ignore the times that, things end up in the third row of the stands. We can ignore the time that our electron happens to be wandering away from that nucleus, because it doesn't happen very often. Instead of drawing this dot picture, instead we can draw a three-dimensional shape. This three-dimensional shape is not always where the electron is. It's just where it's going to be most of the time. Here's the shape of this 1s orbital, trying to capture 90% of the dots in our picture. Does it capture all of them? Well, no, but it's getting at least most of them inside of that circle. There's a few that are outside, but that's just the way it is. We said we're going to codify our orbitals based on the floor that our electrons are on and based on the unit that they're living in, or in chemistry terms, based on their principal quantum number and what we call the angular momentum quantum number for our orbitals. There are two more quantum numbers that we will get to worry about maybe in future courses, but for right now, we can say that there are two quantum numbers that describe our orbitals. If you're trying to codify what orbital that you're talking about, the first number that we see is going to be the principal quantum number, and the letter that we see after it is going to be, well, a letter symbol that corresponds to our angular momentum of that orbital. Without further ado, let's try to unveil what some of these orbitals actually look like. That first principal quantum number dictates the size and the energy of our orbitals. As you go from the first floor of the apartment building to the second to the third, the energy of those orbitals increases and the size of those orbitals increases. This is completely analogous to what we saw in the Bohr model of the atom in the last video. The angular momentum quantum number for our orbitals dictates the orbital shape. So far, we've seen that S shape. This is going to be S for spherical. We can also have that P designation. P here comes as these peanut shapes. Here we have a peanut going up and down, a peanut going left and right, and a peanut going maybe forwards and backwards. You can also have d orbitals. D orbitals have kind of a double peanut shape, or one of them kind of has this donut surrounding a peanut shape. We have these 5 different shapes for the d orbitals. Once we get up to f orbitals, these shapes become pretty wild. Maybe they are flowery shapes, maybe they're quadruple peanut shapes. We got some wild stuff going on here. There's 7 different shapes for our f orbitals. And just reiterate here one at a time. That first quantum number, the principal quantum number, dictates what shell that you have. This can be 1 or 2 or 3 or 4. We've been calling this the floor of the apartment building, dictating what energy that we have. The angular momentum quantum number dictates the subshell. What type of apartment do you have? Is it the S shape, the P shapes, the D shapes, or the F shapes? This also tells you about what we call the degeneracy of our orbitals. Degeneracy means how many come in a set. Our s orbitals come as single orbitals. Those peanut-shaped p orbitals always come as a set of 3. Our double peanut-shaped d orbitals always come as that set of 5. And the flowery shaped f orbitals, they always come as a set of 7. Well, there we go. Thanks so much for tuning in. Hope you all have a great day, and I will catch you next time.